So I'm Keegan. I work at LynuxWorks. I'm a product manager for technology that's relatively new called the separation kernel. We're going to talk about a problem today. It's mainly faced in the Department of Defense, but certainly in a lot of industries that have a security that have a security critical requirement. And we're going to look at that problem and look at all the different factors that kind of add to that problem and how you can use a technology like a separation kernel and this concept of mills, which is something we'll dive into a little bit on how you can solve some of these problems that are quite difficult to solve. The outline of this discussion right here. So first we're going to just talk about the focus of the track, talk about the problem, walk through a lot of the different vectors of the problem, things that really make this a difficult problem to solve, and then introduce how we break this problem, or break this cycle that causes a problem. And then look at this approach that I'm describing objectively, not like a silver bullet approach, but coming into it eyes wide open. You have to really line your ducks up to get this right. And by using this methodology of mills and separation kernels, you really can eat away at some of these major challenges and achieve this kind of long-term goal, which is maintaining these security critical systems. So the major takeaways here to keep in mind throughout this is that a lot of security critical industries like the industrial market, definitely the defense market, sometimes they're forced to trust these low assurance technologies. And it creates a big impact. It's much more than just, I need to get rid of it and get a new one. It really causes a vicious cycle that it's important to really understand, because sometimes you get so tied up into just one of the symptoms and not really look at the big picture of what happened when you start off at low assurance. A key aspect to this is very important, that's why it's very relevant to the Trusted Computing Group, is you really need to embrace COTS. You really need to enter into these solutions with reasonable mechanisms to solve problems at low cost. You just can't say, if you give me $5 million, I'll solve your problem. You really have to think ahead and how to enter this marketplace in a place that's already kind of dealing with the problem. And so COTS is a major component to this. And the last bit is basically applying these COTS components to this with the separation kernel technology and the mills architectural code to really get out of this cycle and get back into what we call more of a secure, maintainable state. So the big problem statement is trustworthy technology is often trusted for use in security critical environments. People just want to use something, they don't know how it works, and they're kind of stuck with it. And when you do those types of things, you're exposed to vulnerabilities that you weren't expecting. If you're, especially in the defense world, you're going to spend a lot of money on trying to give yourself assurance that this technology works when it really doesn't. And you're just really kind of faking it or ramrodding it. It's really expensive to do that. It's also very expensive to maintain those solutions that really kind of started off with this shaky foundation. The expense, too, for recovering for some of the damages that occurred can be sometimes priceless. So one thing that I hear a lot, especially from the NSA, is this concept of the pendulum. Basically, you have some sort of technology, there's a demand for technology, and there's a budget that defense has. And basically, if they apply their budget to really evaluating this technology, they can raise the assurance level of what they're getting, and they can potentially lower the chance of vulnerability, but at a cost of, very expensive cost and very slow mechanisms of deployment. And so here's this pendulum, here's this technology anchored at the top. You're going to just apply resources across this process, and that you could go far right where you do these very expensive evaluations, or you go to the lengths of using mathematics and modeling where you can just kind of prove that it's impossible for the technology to fail, which could be very expensive and potentially off the mark. It actually didn't prove anything. That's a big risk when you go far to the right here. When you go far to the left, you might do something lightly, like just test it out. Does it actually do what I think it should do? Take some security control sets and just say, yeah, this meets all my check boxes, and we get it out the door quickly. So a really cheap mechanism, gets things out the door quicker, but you do have a chance of vulnerability. This is kind of generally accurate, but there's a big oversight, I believe, in this model, where people think if you just apply a process to any old technology that you can raise its assurance level, and you actually can't. If the technology was built to be broken to begin with, just evaluating it can't raise the inherent assurance of the original technology. The only thing the evaluation can possibly do is just confirm whether it was high assurance or low assurance. And so the most important thing is the technology needs to enter with some built-in assurance. And again, going back to why things like the technology TCG brings to the table, you can come into these evaluations at a lower cost and also with a higher level of assurance that allows you to go through these cycles at a much more efficient pace. And we'll go, in the next slide is this cycle. So there's an official cycle where someone selects a non-trustworthy technology, and then you either, you get two branches. You either really put a lot of effort into evaluating it, or you just rubber stamp it. It's too complex to even begin to evaluate it, so you just kind of let it pass through. But either way, if you overpaid for it or you underpaid for it, you're still dealing with a big maintenance headache. Either you're maintaining these artifacts and these things that you built for a high assurance evaluation, or you're just dealing with lots of vulnerabilities. And ultimately, you also repeat the cycle by trying to still use the technology, but fixing symptoms instead of the root cause, which was it was low assurance to begin with. So an example is someone enters a vulnerability in my system because it came from a USB stick, and someone says, well, let's just ban USB sticks without fixing the operating system or the bus protocol of device controllers. And so that's an example where we didn't really fix the problem, so we'll loop around here. We'll try doing something again. The other thing that happens is you get these new markets that are just fixing these symptoms that started with this untrustworthy technology. So you're draining these resources that could be applied to the real, the root cause of this mission is build something that's high assurance. So I just kind of described this. This is the impact of not going in with a trustworthy technology. So what is something high assurance with something trustworthy? It comes from lots of different, you get it lots of different ways. Kind of the best bang for your buck that I believe is starting off with the right design. There's lots of different ways you can architect things, but these are commonly said a lot historically. Building designs that have the least amount of privilege as possible, reducing the amount of code base that might be running in a privileged mode, creating very simple, verifiable architectures. You could add tools to this equation, validation tools, and all this stuff is the vendor, on the onus of the vendor, not the onus of like the government evaluator. So these are great things you can do. Going into evidence, proving things about your code, showing that it really satisfies all the user requirements. And these are things that cost vendors can do. They might not necessarily do them. I actually found this quote from our architect who found it on the internet. It came from a fairly famous computer scientist, Steve Bellevin. Assurance is often what separates actually secure systems from ones that are merely claimed to be secure. It's very true. Anyone who actually writes code knows there's lots of different options to build stuff, and there's lots of ways to open up vulnerabilities that are just completely optional based on the developer's discretion. This guy is well decorated. Professor at Columbia University, chief scientist, technologist for the United States Federal Trade Commission. Great, it's a really great quote. It just came off the NetBSD developer forum. It's pretty timely. So assurance, all those great things that you can do as a COTS vendor, some of those can be extremely expensive, and it's really obvious why you may not bother to do any of those things. So that's an initial challenge to this problem is, how would I expect if I want to deliver built-in security from a cost vendor? Why would they invest lots of money to do things that they might not have even heard of before? So So you might not have been able to afford to perform those mechanisms of raising the assurance. You might not have the time to come to market if you built everything from scratch. The other problem is a lot of solutions require integration. I want to talk to the cloud. I want to talk to my VPN gateway. And if you present a final solution to the end user, it's like I built Fort Knox over here, but it's really dependent on, this kludge that's your weakest link, so why do you even bother putting all that investment into this technology? So the other thing is, especially in the DoD place, you can't afford to go through these really elaborate evaluation processes. So these are very practical problems that you face trying to raise the assurance. So here comes the introduction of this concept called mills and separation kernels. So the idea of a mills architecture is to leverage assurances that are built into a generic foundation called a separation kernel that can host individual COTS components. So reuse Windows, reuse Linux, reuse VPN clients, network stacks, but re-architect these things in a way where you rely on the assurance and the properties of the separation kernel, so you can offload and rely on the separation kernel vendor to say, hey, it was your job to make sure that this memory was isolated. It was your job to make sure that this network device can't DMA into this region. And you made all these artifacts for that, and you got this thing evaluated. Therefore, I don't have to do it. And that's true. That's the goal. That's what we want out of this technology. And so this is this way of breaking the cycle. So because the cycle is there's so many vectors involved. You got the problem where the COTS vendor might really not invest in building anything high assurance. You got the problem where it still might be too expensive to evaluate this thing. And so you need a technology or some way to shortcut this problem. And we believe that the separation kernel and the mills architecture is a way to shortcut this, which sounds counterintuitive to shortcut high assurance, but we believe that it's possible. So some diagrams here to kind of to make an example of where this would be successful, where we would validate that this theory is correct. So if I took some solution, say I had a multi-level problem, I needed to host 2 levels of information. This could be government information, but this could be, like your commercial space where you have private information and public information. And when you look at the overall architecture, there's some component that needs to be shared. Like in this case, we have some disk that's going to be storing operating systems. But the level of information needs to be separate. With a separation kernel implementation, in theory, you can have this thing that hosts these different components. In this case, the most critical component here is this multiplexer, the thing that's going to keep the 2 things separate. And I create this architecture where the dependency of the separation kernel really isn't on the disk itself. In LynuxWorks implementation, it's only on the processor. If I validate that this thing actually upholds its security claims, like isolating memory and controlling information flow, then I should be able to take that certification and reapply it to another platform where it did not impact the security architecture that's designed. And in fact, I also had another nice property where the user space was not dependent on the architecture whatsoever. So that way you have this nice way to maintain the work that you put into evaluating the system such that you can swap out the user space. If one day I want to migrate from Windows 7 to Windows 8, because they didn't contribute to the trusted code base of the solution, you don't really need to reevaluate and reassess this implementation. And similarly, if the disk controller really wasn't linked into the separation kernel, if it really was just controlled by this disk monks, this is the same interface down here. You can even reuse the same disk monk. So there's this idea of maintaining or reducing the cost by reusable components, and that's very important to this argument. And I've talked about this already. So basically a couple of slides ago, the walkthrough here is, how am I going to deliver technology that's really going to support rapid development? How is it going to reduce the cost of my maintenance? How is it going to allow me to go through evaluations quicker? How is it going to lower the costs in these assurance mechanisms? So that's what this next lineage is. So we look at, how do I support rapid development? I forgot these are new slides, so I forgot to add another very important factor here. But number one, COTS, reuse as much stuff that's already been built. That's so important. You just cannot afford to build everything from scratch. Being able to leverage other solutions. Somebody's got something else that's required for my total system architecture, so I need to be able to integrate with those things. The last bit that's missing here is standard support. I guess I have kind of standards in here, but I think that's a higher level thing. Being able to contribute in a community where other folks can also build into this environment protocols and modules and things of that nature to really bring technology to the end user quicker. So the way the separation kernel helps out and the Mills contributes to this requirement of being able to support COTS really is designed to support COTS. So the whole idea is give me a handful of COTS components. Here we have processors, full platforms, operating systems, raw C code, network controllers. Take all those things, create and then compartmentalize them, and use them as building blocks for new implementations. And so an example of an implementation here, I've got this simple encryption implementation where I've got some sort of maybe a surveillance platform that's taking pictures and I need to encrypt them and send them over the internet. In this implementation, I didn't actually add any new. This could be done on a laptop. I take some standard Linux operating systems and I have something that only has control over a camera and it's got isolated resources to take pictures. Separation kernel then can create a communication channel that makes sure it's impossible to bypass this encryption component. This encryption component is very important. It can manage keys, it can run the algorithms. You want to make sure that this thing can't be compromised. It's a separation kernel job to protect that. Finally, you can leverage somebody's off-the-shelf network drivers, so they can other Linux here and use a regular network stack. And if you look at this total design, all of this stuff could have already existed. Someone could, in fact, we've got some work that we're already doing where we've just taken an OpenBSD implementation of a crypto algorithm, ported on a bare metal, put it to a bare metal environment, and the code's already written. So really this is very much a configuration exercise. And so then when you look at an implementation like this, and you say, okay, how is this going to reduce the cost of my evaluation? Well, if this thing's already been evaluated, and this is the only thing that was really important for enforcing the security architecture, the vendor who built the solution didn't really need to focus on that. Sure, his algorithm needs to be correct, but he didn't have to worry about all these side channels like, is this network controller allowed to change the logic in here? And the separation kernel job would say, no, it cannot. So that alleviates the pressure of the COTS vendor to deliver the solution. He can focus on writing an algorithm. He doesn't have to focus about securing the entire platform. Evaluation cost factors. Biggest one is complexity is the number one killer for evaluations. So I've got these two diagrams. One is a marathon. This is the original marathon. And one is a labyrinth. If I were to present a case to an evaluator to say, this is exactly how my system works, and if it's a simple architecture where someone can linearly walk through this thing, and it's literally a code walkthrough exercise. If you do not understand how the system works, you need to speculate, you need to do tests, and you have no idea when you're actually done, you have a full understanding of the system. So when you do have a full understanding of the system, your evaluation procedure can literally just be, well, it's going to cost, the number of the volume of code that you understand, and you just have some labor rate applied to that. If it's complex, it's just an unknown, and most likely it's going to be exponential. You're going to do a lot of trial and error. And eventually you probably won't figure it out, and you're going to get canceled, and then people start basically saying you should never do this again, which is a really, it's very discouraging, especially when parts of that strategy actually had some good elements that should be reused. So it's very important to keep things simple. The last thing that can really contribute, and this is a very important aspect to the cost factor, is being able to reuse artifacts. Like I said, if you certify a separation kernel and you rely on its properties, and you could say you can move across multiple platforms, and those properties aren't impacted by that transfer, that's the goal of this. If that's not true, this is a useless theory. So how does a separation kernel support this? Being small and simple, this is not an operating system. There's no drivers included in this. It's all about keeping things simple, both from a user model and also an internal design. And so from an internal design, we have this least privileged architecture where you remove device drivers out of the trusted code regions, you remove I/O stacks, kernel services, runtimes. You don't need any of this stuff in the privileged mode of the processor. You want to keep the design very simple, very modular, something that you can walk through with an evaluator. Finally, you want to be able to deliver reusable components, either a certification from the past or a standard artifact package. This is something that LynuxWorks has. Is this evaluation package that gives evaluators a deep dive of the product. So maintenance cost factor. This is someone who mentioned this today. I think it was Joseph Allen, where you could get into a project where a vendor tells you a story about this is how much it costs. That looks good, but this is where you go through this iteration of you found a problem, and all of a sudden you need to fix some stuff. You need to upgrade software, hardware. This is where the impact can you have no idea how bad this can get. For instance, there is a bug in that network card. It needs new firmware, but there's actually no way to do it on the ship. So I actually need to either rebuild the whole platform again, or actually will swap out the network card, but all of a sudden I break the compatibility of my user space, and I potentially break the compatibility of a trusted code base, and forcing another whole entire reevaluation. So this is a big thing that can happen. Big cost factor is just the ability to both upgrade hardware and software. If any of these if they're intertwined with both the user space and the security enforcing logic, this is a nightmare. So you want to stay away from this. And so the way the separation kernel supports this is both independence from the user space and the hardware space. Now, there's always going to be a dependency on the processor itself, but you want to reduce that dependency. So, like if there is a bug in the network controller, that swapping out that network controller doesn't actually require any code that goes in the separation kernel that could invalidate some previous evaluation that you've gone through. And same is true with the runtime application space. If you had a virtual machine that actually required a runtime in the separation kernel, and all of a sudden you need an enhancement to that virtual environment, you need some quicker throughput through your virtual devices, and that code's in the separation kernel. If I actually have to make a modification in trusted code base, you have the same problem of impacting this code base that would then force another reevaluation. So you need to be separation kernel, at least LynuxWorks, this version, has this separation of both dependency on the hardware and dependency in the application space. Assurance cost factors, these can be very wide range. Like cost of redeveloping a new product from scratch is just, the vendor would know how much they do it, and usually they would never do that. Doing some tweaks to the design. These are all things that, certainly there's labor rates and also just costs that you probably don't want to go into. So this is where separation can really help, where you just allow you to take some of these things that have already been designed and use a separation kernel to split some things up much quicker. Tool investment, all these cost factors, I imagine, if you would propose this to an actual cost vendor, they'll just say, yeah, we're not going to do that. And I would expect that. So what you do is you rely on the separation kernel to get those assurances for you. Rely on its runtime protection capabilities like memory isolation, device isolation, controlling exactly when things execute in real time, and control all the intercommunication throughout the system. A lot of those problems that you'd have in previous designs really just lack these things, this isolation, protecting critical pieces of code and data, and being able to really define exactly how a machine executes. Rely on the separation kernel to do that for you instead of rewriting your product from scratch, especially if you don't even know how to do it properly. And I just described this. So rely on the separation kernel properties, then leverage them in a design. So one thing you can do is, and we've had examples of this, where you analyze your system, you find out, look at an enterprise solution where a VPN connection a VPN client's integrated in Windows, and someone breaks Windows, and then my VPN connection is subject to my adversary's control. So you can remove that. I can say I'll shrink my attack vector, saying, if I'm only cared about this solution being able to connect to some remote service, I'll take the thing that's responsible for that, remove it from the environment that's subject to subversion, and protect that critical region of code with the separation kernel. Another example is just splitting information levels. If If you want to do virtualization, you want to make sure that one virtual machine can't leak data to another virtual machine. You use separation will isolate all those resources so they can run concurrently without sharing resources. So this was an example. I was going to do a life cycle example of how this would unfold adopting this approach. And so this is a real-world problem. We face it. We support programs that have to do this, where it's very simple. A user wants to run two different virtual environments using virtualization and output audio to an output device, either a headset or speakers. And you need to trust something that you have a security policy You have a security policy that says, one security domain is not allowed to know about the data streams from another security domain. So if one class is spewing out audio streams, the confidential is not allowed to know, and vice versa. So very simple, which is isolation policy, but you're running on the same computing system. And so here's an example of implementation. These exist. These are absolutely deployed in DoD. Where you use virtualization, use some open source technology. You can use Zen, or you can use KVM. You can use Red Hat's VM workstation, VM player, and you basically virtualize these virtual machines, and you run them in process. You run these VMM virtual machine monitoring processes on this operating system. And integrators do this all the time, but a lot of times they lack the knowledge to know what they're really sitting on top of. And so what you're sitting on this application space is this monolithic kernel that has lots and lots of code. And this, we've seen, our experience, we've seen government programs take monolithic kernels that are pure, just right off the shelf distributions from Red Hat. They could have about 20 million lines of code in them, and all of them have access to the same resources that are available in these virtualized application spaces. So if someone were really trying to get in here and analyze, it's impossible for the blue domain to get access to the green domain, this is totally not possible. There's so many ways that this information can be leaked into other across security domains. So this is the audio stack of Linux. You've got multiple layers of kernel space code that one layer is talking directly to devices, but there's all these interfaces that would allow different types of applications to get multiplexed together. And a rudimentary approach is to do things like apply access control policies and try to control these applications in the user space. But really, you got such a big problem in the kernel space. There's just no separation and protection from all this code and data that's being executed. So this is an example where if you try to evaluate this, you're going to have to test this, and that's all you're ever going to be able to do to get verify any kind of assurance of this implementation. And so some of the issues, just I already kind of described them. You're at the mercy of the operating system. If everyone is able to exploit the operating system, find a root escalation problem, or you get root access to the operating system through, or even able to inject code in the operating system, you have no protection of isolation of that information. The kernel space is allowed to access any of that data that those user space processes are processing. Even malicious devices have the ability to access system RAM and potentially write over the logic or read the data and just do whatever it wants with it. You also have a big problem when you're in a monolithic environment. The ability to change the behavior of the driver, those can be as a kind of a tertiary way, or just a mechanism to have something do something with privilege on behalf of something maybe in user space. So these are big runtime protection issues in these monolithic environments. From an evaluation standpoint, you have this nightmare. It's just so much code. It's so impossible to really get the assurance you need to know that the thing works correctly. The other issue is portability. If someone freezes that snapshot, someone's tested it, that this implementation back here. Someone freezes that and says, "Yep, this works. It's good enough," and that might be true. It might work perfectly. The problem is someone wants a new network controller, a new hardware platform that's got a new feature. Those monolithic implementations would require modification to that trusted code base, so you could force yourself to go through another evaluation. The other thing is you could just functionally break the system when you upgrade new hardware. And you also, and it's also true of the application, the direction of the application space. You might need a new modification to the application space. Again, that could potentially impact the trusted code base of the implementation. So you want to be able to isolate these two worlds to get more portability, the hardware dependency and the application space dependency from the security control, basically the trusted code base. So here's a re-implementation of that same use case where the user just needs to stream audio from 2 virtual machines, and it needs to make sure that the data can't leak. So you use the separation kernel. First thing you do is just allocate resources so that they're statically allocated and isolated. So you give the ability for virtual machines to control their own memory and have access to their own CPU, portions of the CPU, basically time slices, or you could assign direct CPU cores to these virtual machines. Run some software, have like basically a guard that can make sure that information can never flow back. So basically, if you do write, so you have this mux here, and you're going to flow data through these diodes, these guards here to make sure that there's no code in here that's allowed to pass information backwards, right? And so this is all done through controlling the memory and writing software such that it's impossible to bypass these one unidirectional guards. Finally, create a safe place to do the critical piece of code, which is the thing that's going to access those levels of information. You care about 2 things. You want to make sure, again, this thing isn't trying to leak data, but really important is you don't want it to spoof audio either. So you need to make sure that however the author implemented this, that it's still authentic. By the time it runs, you don't want people spoofing messages to across security domains that just aren't real. Another little nuance here is with the separation kernel, you can completely shut down the access to a real controller. So there's physically no way for someone to come up with a clever attack where let's just turn on the microphone and let's just hear what's coming out of the speakers instead of trying to attack it at a memory level. So good merits of that design is you got to reuse the separation kernel, you got to reuse Windows OSs, you got to reuse the entire class platform. The architecture is very simple. It's a very simple box and arrow implementation. And the only real investment you did in that design was create this multiplexing app you could potentially reuse, especially you could have gone back here. You might have gotten away with just isolating another operating system here. You could shrink it down, and that might be good enough just to say, since this operating system runs this one application and is a very simple environment, you could potentially validate that that's good enough. And so if you were to do something like that, there would be no investment in the trusted application. You could just use something off the shelf. But the nice thing is, even if you wanted to go that a real high assurance route where the most critical thing you wrote from scratch, put on bare metal is a small piece of code. When you look at the runtime protection of that implementation, you're isolating all the memory to keep the security domains separate. You're also isolating the devices to keep the devices from accessing information from different security domains. You're controlling the execution. Some of you might have heard of timing channel attacks, where you basically try to share multiple devices at the same time and derive information. Basically, look at how something's utilized, look at the pattern something utilized. With the CPU, with a cyclic timer, you could actually control when things run. So, depending on the design, you could actually mitigate certain attacks. Those are pretty advanced, but they certainly exist. Other protections that are built in the separation kernel is the ability to monitor the hardware platform, make sure that the things that it relies on and enforce their properties, you continually monitor that. You could even do some lower level control, like control the attributes of the cache, either for performance reasons or again for security reasons. You could, and even in a configuration space, define what types of memory regions that you'd be using in architecture, whether or not you're allowed to execute memory in those regions. Extra control that just gives you, allows you to implement stronger assurance implementations. Finally, information flow control. You have to know how all the information is flowing through the machine to guarantee that your system upholds some security policy. The simplicity of the design is very important for an evaluation. You just present an evaluator. I got boxes and arrows. One virtual machine passes data to this diode makes sure that no information is allowed to go backwards, and there's this mux over on the right that just mixes the two together and spits out our audio. An evaluator says, yeah, that's very simple, and then what you can do is then here's the thing that's responsible for enforcing the directionality of those information flows and also the protection of all that data. It's a separation kernel, and so you deliver some standard off-the-shelf package that describes the property separation kernel that should be generic, and you should be able to be reusable across evaluations. The other thing is the upgradability of that design. The Windows environment was completely independent of the separation kernel and even the mux, so you could upgrade those virtual machines without introducing any impact to your trusted code base. The hardware independence, you could have added more devices in that architecture if you needed, like to give those virtual machines access to network cards. You can do that without having that impact the separation kernel. The separation kernel doesn't have device drivers, therefore that architecture you created, adding the presence of a network card doesn't impact what you've evaluated in the separation kernel. So there's a story of being able to preserve what you've evaluated in the past, even when you want to upgrade or make some modifications to your architecture. This is a summary. This is very important. Not all separation kernels do this, and this is also very important and realistic. In order to support rapid development, achieve these claims about reducing the cost of maintenance and being able to achieve higher levels of assurance, it's very important that virtualization is supported. If you can't just take another operating system and run it, then you're going to deal with a lot of problems. No one's going to enter any kind of project with you if you're going to tell me you have to write a new operating system. And you have to be able to support COTS hardware. No one's going to start a project with you if you have to build them a new board. Maintenance, this is critical. You have to have some level of independence from the hardware and application support. If anyone wants to mature their design, add new capabilities by being able to split the dependency of the application runtime from the privilege or the trusted code base, and then you enter you get in the case where you have to reevaluate the design. So splitting those up would really allow you to have a longer life cycle of the technology while keeping a mature security architecture intact. And then finally, the assurance is very important. That one of the most important things about this, these are kind of these side effect things where you want to reduce the cost to build this stuff, but in the end, I also really want a secure product. So I want to make sure that the thing that I'm relying on is not yet another monolithic kernel. So even if I came up with this really a separation kernel that does have some level of hardware independence, it does split up the virtualization runtime, it does isolate memory. If I find out that thing is 20 million lines of code, that doesn't help out, because that evaluation is going to cost a whole lot. You're going to probably have a lot of bugs in there that potentially could allow people to exploit and get access to the root to the privileged mode of the processor. So all these kind of properties need to be true about the separation kernel to really support this idea of quick path to assurance. Closing statements. In summary, when you look at this cycle of, when you enter in, this vicious cycle of overpaying on evaluations, dealing with symptoms, it all starts with having untrustworthy technology. So you really need to break that cycle, delivering some trustworthy technology from the start. Separation kernels, we believe that's and using those architectures, this idea of reusing COTS components and creating new architectures that have higher assurance. That's a quick path to breaking that cycle. I want to put these teasers out here. This is also something that's been going on. We've been working on standards, and that was one of the things that I forgot to really highlight, the importance of standards. So we have two standards going on. One is called distributed mills, and one is called dynamic mills. The distributed mills is very much like the Trusted Network Connect. It's the idea of, if I want to go look at one of those architectures again, looking how the information flows from the machine, looking at how I isolate memory, I could describe the behavior of that machine, and I could measure it. I could say, yeah, that's a good implementation of something. And that's very important if you wanted to support some high-level protocol, like a VPN connection, and I started articulating the property of the system. Not only do I want to say it has some hardware features or some features in the operating system, I want to say, hey, it was actually a good implementation. So you could reason about the configuration of the machine and distribute it across nodes, and they can actually leverage that information as part of their decision making to whether or not they want to connect with each other. This was a snippet out of one of the just kind of descriptions of one of the goals of using dynamic mills. It's really targeted for those critical markets, safety and security. So the idea is presenting these assurance cases that allow you to argue about whether something's dependable, like safe or secure, based on how it's kind of composed, based on the architecture. And so if you create this broad definition of how the system's composed, you might be able to reason whether or not something is really fit for running critical environments. And these were some of the customers that are targeted, the aerospace mainly. Dynamic mills is a complementary technology, is another standard that we're working on that adds this element of polymorphism. So if you were to come up here and see the configuration doesn't fit your needs, you might want to change it. You need a secure way to change it, as obviously that adds more complexity. But the idea is to really have a high assurance mechanism to change the behavior of the machine. It might be for reliability. You might want to, if you have like a network device, you might want to be able to select different transports, like using Ethernet, Wi-Fi, or 4G wireless technology. But it also might be for resiliency. You could look at a configuration of some implementation of something, and you might say, hey, that's not a high assurance implementation. That thing is subject to some DMA attacks from this network device. So you might want to reconfigure it or change the way you want to connect to stuff. So that's it. I'm done. Any questions? All right. Thank you.
Thank you, Will, and thank you, loyal attendees. That concludes our activities for today, but we will be wrapping things up tomorrow with a panel and a keynote starting in here at 9, and we will have breakfast, of course, in the exhibit hall at 8 p.m.